This week we're going to learn yet another technique for solving for the electric potential, which we can use to find the electric field for a particular charge configuration. This week we're going to learn a technique called separation of variables, and I'm going to try to split up, they're kind of long problems, so I'm going to try to split them up into smaller videos. The learning goal of this particular video is to learn how to simplify the solution of a second order partial differential equation, which is what Laplace's equation is, by manipulating it so that each term that you're adding together is a ordinary differential equation depending on one variable. And I'll show you why that simplifies your ability to solve those problems by hand. Okay, so I just wanted to warn you guys, for these lectures, we're going to start venturing into some kind of, I think, hard mathy parts. I mean, I think the class has had some hard math in it all through, but now it's going to get particularly complex, okay? And I just want to remind you guys, this took a lot of very smart people a long time to figure out. So have patience with yourself as you're trying to understand it. Take it slow, and remember, a lot of this stuff, you know, like I said, you don't necessarily need to be able to have come up with it from scratch, right? You just need to understand the technique that someone else probably spent years trying to figure out the origin of, okay? Which is to say, if you were to give in some of these examples, it's not really up to you to know, oh, this is the right technique to solve for that particular example. But if I gave you an example and you knew that you were going to use separation of variables, you need to be able to kind of go through the steps that I'm going to show you in order to set up the problem. And we're going to start off with a two-dimensional Cartesian example of what we're doing, which is separation of variables. I'm going to cheat a little bit, and I'm going to take the image from some notes that I made before, so you guys don't have to watch me struggle to draw it, but you could pause the video and draw it yourself. Okay, so I'll describe this in detail in a second, but I'm going to call this a semi-infinite metal plate taco. It's kind of like one of those flat shell tacos, okay? But just to describe what we're looking at here, I'm going to zoom in. Okay, again, this is the same example from your book if you want another version of the figure. But I've drawn a coordinate system. Z is in this direction. X is kind of cruising in between these plates in green, and Y is perpendicular, of course. Okay, and these green plates here are plates that extend out to infinity in the positive and negative Y direction and in the positive X direction. Okay, and they're also grounded, so that means that they're set at a potential of 0. So this one has a potential of 0, and this one has a potential of 0. Okay, these two plates are separated in the Y direction by a distance A. Okay, so they've got some gap between them. And then on this edge here, they actually end in the XY plane here. And in the Y direction, along this plane, there is a strip with a width of A, and this strip also has an infinite length in the in the positive and negative Z direction. And this strip is different from these strips in that it is set at a voltage, which is to be specified, but it's called a hot strip because there's some voltage applied to it. Okay, and it's insulated from these grounded. Okay, so the first step is to use the picture to define our boundary conditions. All right, so let's go ahead and do that. Okay, and actually I'm going to label this as step 1. All right, so if I'm looking here at the picture, I know I have a voltage equal to 0, okay, when Y is equal to 0. So anytime I've got a coordinate where Y is equal to 0, that's going to be in this ZX plane. So I know that I'm going to be on this plate here, and the voltage is going to be equal to 0, okay? Same thing if I go up to this plate here. So if I'm at y equals a, that means I'm somewhere on this green upper plate. So I know the voltage is 0. Okay, that's 2. Here's another boundary condition. I know that the voltage is equal to whatever that hot plate is set at. Okay, when x is equal to 0. Okay, so that's going to put me, when x is equal to 0, I'm going to be over here on this plate. Okay, and the last boundary condition I don't really get out of the image here. It's something that I have to assume. But if I'm getting really, really, really far from this hot plate, really far in the x direction, I think it makes sense to assume that the voltage or the potential is going to go to 0, okay, as x goes to infinity, okay, because we're going to be far from our V0 plate, or that hot plate, okay? So these are the boundary conditions, and these are really important to define first. These are really what are going to define the solution or the foundation of our problem. Okay, so in between the plates, there is no charge, so our rho is going to be 0, okay? So we can use Laplace's equation to solve this particular problem, okay? And we're going to use Laplace's equation to solve for the potential in between the plates. Okay, so just in between the plates, Laplace's equation looks like this. Okay, I want to simplify it a little bit, and it's always good to simplify right in the beginning. And in particular, I want to note that the solution cannot have a z dependence. Okay, so if I go back to the picture here, that's basically acknowledging that as I move out here in the z direction, okay, because these are infinite plates, all of these plates extend to infinity in the plus and minus z direction, at a particular x and y, okay, so the y is going to tell me how close I am to these grounded plates, the x defines how close I am to this hot plate, but at a particular x and y, it doesn't matter what my z value is here, okay, because this particular hot plate, the voltage on it has no dependence in the z direction. It's going to be constant in the z direction. So really, if I was in here, I wouldn't be able to tell where I was in z space. Everything would look the same, whether I was at z equals 0 or z equals 100, okay? So the solution can have no z dependence. So that just helps me simplify the solution that I expect to get. So instead of getting a voltage or a potential that depends on x, y, and z, I know my potential is just going to depend on x and y. And therefore, I can take Laplace's equation here and I can simplify it a little bit. And now it's just going to be the partial derivative of the voltage with respect to x and the partial derivative of the voltage with respect to y. That last term would be 0, okay, because whatever voltage I have, it's not going to have any dependence on z. So when I take the derivative, I would get a 0 anyways. Okay, so I can just say this is equal to 0. So I've eliminated a term. That's going to make the solution or the problem solving simpler. Let's do step 2, which is assume a solution of the form. Okay, and this will be a pattern, but basically you're going to assume that the voltage is going to be equal to the product of two functions. This is a big X. This is a big Y. Okay, the product of two functions that just depend on X and Y. Okay, so this is the product of two functions that just depend on X and y. Okay, so this is hopefully gonna, this is the starting the separation of variable process. This is gonna simplify things. Okay, so the next step is, once I figure that out, okay, I'm gonna plug assumed solution into our equation, Laplace's equation. Okay, when I do that, I end up getting, let me just do it real longhand here. Okay, that's that first term. And that's the second term. Okay, I'm going to go ahead and take those partial derivatives. I'm going to go ahead and pull out. Notice because here, if I look at this term, y has no x dependence, I can go ahead and pull that out. And that leaves me with this. And the other term is going to look similar. Okay, that's all still equal to 0. Okay, let me go ahead. I'm going to need to copy this over to the next slide. Okay, the next step is going to be to divide by our assumed solution, which was those two functions that just depended on x and y, the product of those two functions. When I do that, okay, my version of Laplace's equation here is going to be transformed. Okay, notice here I'm now going to write my partial derivatives as ordinary derivatives with respect to x and y. Okay, and I can do that now because the functions that I'm taking the derivative of, they don't have any dependence on a variable other than x and y. Okay, so by doing that, I've done the essential step of separating variables. I've got two terms here, okay, that are now ordinary differential equations that just depend on one variable, okay? But why? Why bother? Okay, so now we're going to see what that gets us, okay? All right, so just like the book describes, I'm going to let the first term be called a function f of x. So it's a function that depends on x, and that's going to be equal to 1 over big X times the ordinary derivative of big X with respect to little x. Okay, just to make that clear, these are big X's. I'll put some things on there so you can tell. And this guy is a little x. Okay, and I'm going to let another function, which I'm going to call g of y, and that's going to be equal to 1 over the big Y, okay, times the second ordinary derivative of big Y with respect to little y, okay? That allows me to rewrite the Laplace's equation as something a little bit easier to write, okay? This function here plus this function here is still going to be equal to 0, okay? And now we need to do a little bit of thinking. So these two guys, when you add them together, they have to sum to 0, okay? It's important to note that if f of x changed because x changed, okay, so I moved to a different x, there is no way my other function here, this g of y, could compensate and cancel, okay? And that's because it has no x dependence. So it won't change if x changes. Okay, it'll still be in the same value if I move in the x direction. Okay, so this tells us that in order for this sum to always be equal to 0, our f of x and our g of y, they have to be constant. Okay, they have to be constant, or else they wouldn't always sum to 0. Okay, so that's important. These two guys, I know they have to be constant because the sum of them is 0. All right, so that's getting us somewhere. Okay, so now I'm going to define new constants. Okay, so I'm going to call them C1 and C2. They are constants, which means they're not changing. I'm going to let this guy, the big X, the first term there, which was 1 over big X, the second derivative with respect to X, I'm going to let that be equal to the C1 constant, and the other term, this is going to be equal to the other constant, C2, and of course I know that if I add those two constants together, they're going to sum to 0. Okay. In this particular problem, okay, we know that C1 is positive and that C2 is negative. How do we know that? Pretty much because we've already solved this problem before. It's an example for a reason, okay? But maybe if you were solving this for the first time and you didn't know to assume that this was positive and this was negative, you would start going down a path, right? Maybe you would assume it the other way, or maybe you just start solving the problem and it would reveal itself to you. And sometimes that's how physics goes. You just start kind of working your way down a solution and you realize, ooh, I took the pathway, basically. I got to go back to this step where I could have gone one way or the other and I need to take the other branch. So, all right, so if that's true, I'm going to define a new constant. I'm just going to call it C. It's going to be equal to C1 and it's going to be equal to the negative of C2, okay, which is to say that C2 would be equal to negative C. Okay, and I'm also going to let this constant C be equal to k squared. And that'll become obvious why I'm letting it be equal to k squared, because the functions that I'm going to assume for x and y, I'm going to be taking the second derivative of them. So the constants in those functions, they're going to be pulled out twice for each derivative. Okay, so where are we getting here? I told you that this technique would make differential equations easier to solve. Okay, I've got Laplace's equation now is been separated into two ordinary differential equations. Okay, so I've got ordinary differential equations. Okay, I can look at either of these independently now because I've again separated my variables and I can assume a solution. All right, the first one looks like this is a big X. This is our little x. Okay, if I simplify that, it's going to look like k squared times the big X. Okay, and our second one is big Y, little y, and that's going to be equal to negative k squared times big Y. Okay, now again, I'm going to look at these two. I'm going to use what I already know about differential equations, and I kind of know the first one has the solution that big X function with respect to X is equal to some A times E to the kx plus another constant b times e to the negative kx. Okay, I don't know what a and b are, but I can figure that out using my boundary condition. Okay, and why do I know that this is the solution to this particular differential equation? Well, I don't want to waste time plugging it in now. You can do that if you want. But if I do plug this x value in for x here and take two derivatives, okay, I want you to notice that it would stay positive with our two derivatives. Okay, so that means I'm not going to get a negative sign out front here. So I know that's the right solution for this one. This second order differential equation looks similar, but I get a negative sign pulled out. Okay, so that one has a different solution. For that one, I get big Y, Y is equal to C times the sine of KY, okay, plus D times the cosine of KY. Okay, and again, I don't know what C and D are. Those are constants that I'm going to have to figure out using my boundary condition. But this one, it does change sign with two derivatives. Okay, so I know that's appropriate for a solution to this second order differential equation. If I plug this guy in, and take two derivatives, I'll get a sine back for this first term, but it's going to have a negative out front. I'll get a cosine back for the second term, but it's going to have a negative out front. Okay, so that would make sense with this negative sign in this particular second order ODE. Okay, so let's put that all together. Okay, that gives a potential that is, again, we assumed it was equal to the product of those two functions, big X and big Y. Okay, when I take the product, I get and the second term okay, and the next step is to figure out constants using boundary conditions. Okay, and I'm going to stop this video here and we'll pick that up in the next video.